So I was talking with ChatGPT the other day, and I was annoying him. I asked him for the difference between a sine wave and a cosine wave, and he goes down this yap session of just like all the reasons. There's like that reason, and then all those reasons. Um, Sorry, when I have a whiteboard right here, I feel the need to use it even when explaining stuff like this, and I don't think this accomplished anything, so I'm just gonna not do that during our explanation. And obviously I know the difference between a sine wave and a cosine wave. The thing is, a cosine wave is just a sine wave, but phase shifted. So I try to explain that to him, and he's like, sure, you're right, with a small caveat, it's kind of not a good thing to just make them the same thing, because they have their independent uses. I'm like, okay, yeah, but I'm still right, because sine wave is anything of that form. So I'm right. And then he's like, yeah, sure, whatever. And I'm like, okay, so you want to play it that way. Integrals are just sine waves. And he's like, no. Although, I will point out, he was very sycophantic, and that is such a problem. He tried coming up with some weird line of reasoning that would have made what I said smart, but what I said wasn't smart, and this is a problem, because you see in the news all these kids doing just terrible things because of ChatGPT's encouragement. And it's a problem that needs to be addressed, like, as soon as possible. Oh yeah, and I think I also told him that, like, lambda functions from Python were just sine waves. And, yeah, he didn't let me get away with that one, so that's nice. And then I thought this would finish the conversation. Math is just a sine wave. And he goes, well, not really, because you have that. I'm like, okay. Give me any problem, and I will solve it using exclusively sine waves. He told me, prove that there are infinitely many prime numbers. Challenge accepted. So how on earth are we gonna do this? Well, I'll get two things out of the way. First thing, I will be allowing myself to use basic operations, because you can't do much without basic operations, and pretty much anything you learn at a level lower than, like, trig, so we'll say geometry, because we're only really doing writing. It's more, no, so it would be more like pre-calculus, I guess, but we'll just say anything below geometry is fair game. And I am going to include this symbol. What is this symbol? Well, it's capital pi, but essentially it's a product, right? So let's say we have this. This is going to be equal to, it's like a summation, but with a product. For some reason, this is less known. But you plug in n equals 1, then you multiply by the next term, you plug in n equals 2, and then you're going to multiply by n equals 3. So we get, this is equal to 6. Point is, yes, that is technically a calculus concept, but technically I can just write it out as multiplication, technically. It's just compacting things and making things neater. Like, don't let that discourage you. This is still really, really cool. And we'll actually be using only two main axioms about sine, which first is the zero set of sine. If sine of pi times x is equal to 0, well, that's true if and only if x is an element of z, or x is an integer. And our second fact we will be using is that if sine of pi times n over p is equal to 0, well, that's true if and only if p divides n with no remainder. And you can actually see this, because if p divides n evenly, then this just becomes an integer multiple of pi equaling 0. So, yeah, those are our two axioms we'll be using this entire time. So, let's get into it, because I've been talking for a while. I don't know what that was. So, the first thing we're going to do is we're going to make an assumption. Our assumption is that there are finitely many prime numbers. Obviously, you should have known that by now. There are finitely many prime numbers, and I'm going to show you why right now. That's a joke. We're going to show you why this isn't true by assuming this. So, this is our list of prime numbers. It's finite, because this is our last one. I'm not putting the dots on forever. Prime number 1, prime number 2, and we got couple more primes than our last prime, because there's finitely many. So that's our list. And now we're actually going to make a function. Let's define f of n as the product from I equals 1 to k. So we're going to cycle through all our finitely many primes. And then this, what we're going to be producting, or multiplying, or I don't know how you'd say it, is the square sine of pi times n divided by pi. What does this function detect? Well, if any prime, p of I, divides n, well, then that means that the sine of pi over n divided by pi is going to be equal to 0. Remember, that was one of our axioms about sine. But since this is a product, that means the entire function will be equal to 0. So essentially, if any prime p of I divides n, this is going to mean that our function is equal to 0. If no p of I divides n, then our entire function is going to be non-zero, greater than 0 specifically, because each of these terms will be regular sine term. And the reason we have squared is that way if the term is negative, it becomes positive. So we can say that this product is going to be strictly greater than 0, not just not equal to 0. And that's very handy for our proof. I'll write this out over here. Now, why did I write this star right here? Well, that's just another way of saying that in each case, you just replace the star with this sign. Is that actual notation? No, I made it up a long time ago for stuff like this, because for some reason there's not an easy way to write it. But yes, it's basically just a piecewise definition, but with different signs. I find it very helpful. I should probably have looked if there's actual notation for that, so I might be angering a lot of you guys. But anyway, yes. Here's where we run into problems with there being finitely many primes. If these are all the primes, then every integer, n greater than 1, is divisible by at least one of them. Now, this is just a fact about primes. Every integer greater than n equals than 1 is going to be divisible by at least one prime. What would that imply? Well, if every integer n greater than 1 is divisible by at least one prime, and these are all the primes, then that means one of these terms has to be 0. So we have the fact now that f of n must be equal to 0. So we have this fact now. Now here's the problem. Consider the following integer. P of 1 times P of 2 times P of 3 all the way to P of k. We now have all our primes right here. But then we add 1. And let's let this integer be equal to a. None of these primes right here divide a. None of them, which means sine of pi a over pi is never equal to 0, which means f of a is strictly greater than 0, but we know f of n has to be equal to 0, and thus we've reached a contradiction. These two facts cannot coexist. In fact, they're written piecewise right here, which means we've proved, well, the only possible thing here that could have gone wrong is that our assumption was incorrect, because, well, it's an assumption we made, and all the other stuff follows directly, and we've reached a contradiction. These two facts cannot be true at the same time, and therefore, we have just proved that there are infinitely many prime numbers, because if there's not finitely many, there's infinitely many.